Okay, so picking back up on this molar mass problem here. So some people are going to be, maybe a little more comfortable with sort of abstract math and be pretty comfortable rearranging their equations. So back up the page here, plugging in mass over molar mass for n, rearranging the equation here to solve for molar mass. If you're not quite so comfortable with rearranging an equation like that, you can solve a lot of these problems just by dimensional analysis, or just by figuring out the correct units. So in this particular example, so let's use this one as an example, we're looking for the molar mass. If we recognize that molar mass is grams per mole, if I take all of the relevant information from the problem and put it together in a way that the only units left over are grams and moles of the same gas sample, then all the other units cancel out. I will have reproduced the same calculation. So for this particular problem, right, if I just start with the idea of I need to get grams on the top, I could start with the density provided in the problem, 7.135 grams per liter, right? And I've got grams, and let me put a circle around that because that's a unit that I want to keep. I don't want to cancel that out, but I want to get rid of liters here. So I want to look at the rest of the information I have for the problem. What can I use to cancel out liters? I don't have any other volume information, but there is liters in my gas constant, 0.0821 liter atmospheres per Kelvin mole. So if I put that gas constant in next, 0.0821 liter atmospheres per Kelvin mole, I have now canceled out liters, right? Just like we do with dimensional analysis. Now, I've also introduced a lot of other things. I've introduced moles on the bottom, which is also good because I do want that. I want grams over moles. But I have extra or extraneous units now to kelvins and atmospheres. So it's not the molar mass if it's atmospheres per K along with grams per mole. So let's get rid of those other units. If I multiply by the temperature, I can get rid of Kelvin. So I multiply by the fact that this gas sample is at 285 Kelvin. That gets rid of Kelvin. And now I need to cancel out this atmospheres, which is on the top. So I'm going to divide by the pressure. So if I have atmospheres on top and on the bottom, those cancel out. Now all that's left are the units I was looking for, grams per mole. And I can do that without the formula. Now, if we actually look, this is exactly the same as the problem was set up when we did use the formula. In fact, that's where the formula comes from, is the way these units work together to cancel out. So really, this is what would come first, and you would figure out what the formula is from the way these units cancel out. But if you're comfortable with the formulas, that can be a pretty easy way to approach these problems. If not, you can use dimensional analysis, right? Just make sure you're setting your units up correctly, right? I do see people put the fractions in a weird way. Like you put the whole density on the top of the fraction, and you're off to a really complicated start with your units. So put it in a way that's easier to understand. Now, if we do punch this all in, of course, we would get, it's the same exact numbers, we would get the same exact answer. So something to keep in mind as you approach some of these problems, that the units are your friends and can help you work through a lot of these problems. Okay, a few other issues with gases. So far we've kind of talked about one gas, right? Or we talked about air at one point, which is a mixture of gases, but we just were looking for how many molecules were in the sample. But we may have more than one gas together in a sample. This may come in when we start to look at stoichiometry or chemical reactions that have involved gases. But it could just be a set of gases mixed together. So there's an idea called Dalton's law of partial pressure. And it's stated as shown here on the page, the total pressure of a mixture of gases, so P total here, or P subtotal, is equal to the pressures of all of the gases in that mixture. So the total pressure of a mixture of gases would be equal to the pressure that is produced by the first gas plus the pressure produced by the second gas plus the pressure produced by the third gas, etc., for however many gases are in the sample. So gases actually behave in a very straightforward manner. You can add their pressures together. That will give you the total pressure of the sample. Right? So this is pretty straightforward. You calculate the pressure of just the oxygen in a sample. You could add that to the pressure of nitrogen in the sample or whatever else is in the sample. Okay? So if we look at the example here, right, it's a PV equals nRT problem. It just has multiple gases. So we have a mixture. It's got some helium, some neon, and some argon in it, but it's all together in one 7-liter vessel at 25 degrees C. We want to calculate the partial pressure of each gas in the mixture, so the pressure that's coming from each gas, and then we also want to calculate the total pressure. So if I want to calculate pressure and I have moles, volume, and temperature, I can do that using PV equals nRT. To solve for pressure, I just want to divide both sides by V. So that would be the pressure is going to be nRT over V. Now, we want to do this for each of the gases, so let's start with helium. So the pressure produced by the helium, so that was just the first one given in the problem, that's going to be how many moles of helium there are, 0.477 moles. Times our gas constant, 0.0821. Now for this problem, I'm going to leave off the units on R just for space reasons, right? But that is something useful to keep in mind, particularly as you're practicing. It maybe will help you get in the right set of units. But because we are leaving them off, we need to be really careful about our units here. The temperature has to be Kelvin, so 273 plus 25 would be 298 Kelvin. That's the kind of thing you're likely to forget if you do leave your units off R out of laziness as opposed to trying to make it fit on the page. The volume here is the correct set of units is 7 liters. Okay. Now, because of the units on R, this will end up giving me pressure units or atmospheres. So the partial pressure due to helium, I can calculate by just plugging this in. And this comes out to be, now it would be 3 sig figs, so 1.67 atmospheres of helium. Right now, this is a separate answer we were asked for, so I'm going to round it to 3 sig figs. If we just wanted the total, we might want to save some extra sig figs for adding them together. Now, we need to do the same thing here for the other gases. What would be the partial pressure of neon in the sample? Now, I'm switching colors here because we want to recognize some similarities here. Everything up here is going to be the same except how many moles of that gas there are. It's the same gas constant, it's the same temperature, it's the same total volume. So if I just plug in the 0.280 moles for neon up here, I'm just doing the same calculation with 0.280 instead of 0.477, which was moles of helium. So I don't need to rewrite that whole thing if I recognize that. And punching that in, the pressure due to neon is 0.979 atmospheres. Right? And the third gas in the sample, argon, I can do the same thing. I just need to change to how many moles of argon are in the sample. So I do that in the purple. And that is the partial pressure due to argon is 0.384 atmospheres. Right? And then again, according to Dalton's law of partial pressures, the total pressure will just be the combination of all of those. So the total pressure in the sample, I just need to add those three up. So 1.67 plus 0.979 plus 0.384. And because of the rules for adding for significant figures, I've got to stop 2 places past the decimal, because that's where the last significant digit in my helium pressure was. So even though my calculator says 3.033, I got to stop at 3.03 atmospheres here for my total pressure of this sample. Okay, so multiple gases, right, it does make the problem a little more complicated, a little more to look at, but the way the gases, their pressures add together is going to be fairly straightforward. And it's helpful to recognize pressure and moles, right, on opposite sides of the equation here are directly related. If you have more moles of gas, you'll have more pressure. So you can draw a direct relationship between those two quantities as well. So sometimes you might want a ratio, right? How much of my sample is made up of a particular gas? If that's the case, it'll make up that much of the pressure of the sample. Okay, we'll have to call quit to the video there, and we'll pick up on some stoichiometry as it relates to gas laws in the next video.